So in this case, we are going to consider our alternating current theory, which is the AC theory in short. As we are to consider our AC theory, it is important for you to understand the basics on the generating of an alternating EMF. An alternating EMF, as we had or as we have the alternating current, the same thing, the alternating EMF. We have these basics, guys, from the previous levels that we had from our N4. We have been talking about this part of the alternator. An alternator, which is an electrical generator. Remember, an alternator. So we are going to consider an alternator in this case. So it is an electrical generator that converts mechanical energy into electrical energy. So this one, it is going to convert mechanical to, all right? So we're going to have mechanical energy being converted to the electrical energy. So it is just like a consideration where we dealt with the generators. Remember when you dealt with the motors, generators from your N4, like I said, where the input is mechanical, all right, mechanical, and the output is electrical. So this is the consideration of an alternator, that is the use of a generator. So considering that, if we are to have these guys, we have to go back to the Faraday's laws of electromagnetic induction from the previous levels that you dealt with in your N4, and for those actually from N2, guys. This is from N2, so I'm not going to dwell much because this is actually our N2 stuff. So I'm just going to have the basics. Remember the sinusoidal waveform. So here, I want us to consider the part of the Faraday's law before we move on to the sinusoidal waveform. We understand that when a conductor or a coil moves or cuts across magnetic flux, an EMF is induced. Remember, we are talking about what? The generating of an alternating EMF. So that is the induction. The EMF is induced in the coil or conductor. So that is the condition of our Faraday's law of what? Electromagnetic induction. So I want you to just go back, guys, revise the basics, N2, N3, N4, so that it can be best in your understanding, and also the understanding of a sinusoidal waveform. All right, this is another part which is important, okay, as we have our sine wave. That is a sine wave from our mathematics, all right? We understand this in a mathematical way, a sine wave. So we are saying the induced EMF produces current flow once an electrical load is connected across a coil. Both current and EMF are alternating values, take note, and are represented as a sinusoidal or a changing waveforms. This is the idea that we have. So from our mathematical presentation, guys, we understand from this sine wave that we have from the input up to the end, depending with the number of cycles that we are going to have. So this one, we consider it as a complete cycle in what? 360 degrees. So the EMF or the current, which is under the sine wave, they are going to experience values. As we understand our sine wave, guys, this is the maximum value that you can ever have, which is also corresponding to this side, the minimum value. So the values, they do change from one point to another, from one point to another, until they reach the maximum value. They start again to reduce until if a zero, they reduce minimum value, they go back until this point. So we have values changing from one point to another until we reach the maximum value. So these values are referred to as the instantaneous values. If we are referring to the EMF, the instantaneous EMF, if it is current, the instantaneous current, that is values that we have at a particular point or at a particular section or at a given time. The values that we have at a given time, then we've got the maximum value. As we can see from a sine wave, we do understand that is at 90 degrees. That is where we've got maximum. And at 270, we've got what? The minimum value from our sine wave, guys. We understand this. So I'm not going to dwell much into the theoretical part. I want you to go through that as an individual, understand the theoretical part that we are given. So what I'm going to simply do is to have some mathematical presentation of our AC waveform. All right. So this is another part that is important. Our AC waveform that we have, which is the sine wave, but we need its mathematical representation or mathematical expression. All right. So the mathematical expression can be given, as we do understand from our mathematics, guys, a sine wave, it is the sine of theta, like we're given y is equal to the sine of theta. So if you're given another value, it can be 2 sine of theta. We also saw that from our mathematics, it can be given as 3 sine of, then we can have a certain angle added to that theta. It can be theta plus 45 degrees. So it is just that understanding that we still have of this being the maximum value amplitude. All right. The angle of 45 degrees, which is the angle that is being added to the original part that you were given. So all that part. But in our electrotechnique, so that we do understand this, we are going to have this in the form X is equal to X max, which is the maximum value of that quantity that you are given. Then the sine of omega t plus or minus alpha. So I'm going to explain what this mathematical representation means. X being the instantaneous value. For an example, it is the current. We're going to have the maximum current. So that is the idea. So since we are just focused on the EMF, let us just say E is equal to, then this is going to be E max. This is the maximum value of the quantity. The sine of omega t, omega, which is our angular velocity that we are given. Remember our angular velocity in science, mathematics, omega being measured in a rad per second, rad per second. So remember, if you multiply omega times time, this is our displacement from our angular displacement theta. It is the product of what? Omega and time. Remember, omega is equal to theta over time. Isn't that the product? So this product here that we are seeing here of the omega and the time, we can even take it from the units, guys. Rad per second means rad over, remember, per second over a second times the time in a second. So you multiply by that second. What's gonna happen? They cancel. You remain with the rad. So meaning to say the whole of this part combined together, the omega t that we see there, combined together, it is an important thing that we do understand, that we must understand. It is in radians, the whole of this part. The whole of this part, omega times time, gives us the radians, which is our theta, our angular displacement. That's our angular displacement. All right. This alpha that we have there, it is already in radians. It must be in radians. Since this is in radians, guys, this is addition and or subtraction that we are going to have. We're going to add or subtract. So for you to add or subtract here, these are supposed to be same units. This part here and this part are supposed to be same units. This part supposed to be same units. So if you decide to use the radians, make sure that your calculator is in radians. If you choose to use the degrees, make sure that your calculator is in degrees. So that is the idea there. These two are to be added. You cannot add 2 pi radians, then you add to 30 degrees. This does not make sense. These are supposed to be the same for you to add. If it is 2 pi plus 3 pi, it's fine. If it is 30 degrees plus 40 degrees, it's fine. Same units. This is what I'm trying to say. So that is the alpha that we see there. It is also an angle, just like the whole of this omega t, the product, this of omega t. So guys, let us go back to our mathematics. All right, so I think that's it from this part. All right, let us talk about this. All right, let me finish here. So I was saying it can be given as E is equal to E max sine omega t. All right, plus or minus alpha. Let us go back to the omega again. The omega that we see again, separate. Now we want to take it separate. Remember, this is our angular velocity. Our angular velocity in rad per second. All right, let me do this. Angular velocity in rad per what? Rad per second. We do understand that omega is equal to 2 pi f. So therefore, from the omega frequency can be determined. So therefore, we can have frequency there. Divide by 2 pi. So that's omega over 2 pi. So that is, we can have our frequency from there, which is measured in hertz. So that's it. Play around with these formulas. And remember the time from that sine wave that we have, the issue of the period, this and that. So the time as it is calculated as 1 over the frequency, it simply means it is the reciprocal of this. If frequency is omega over 2 pi, the reciprocal, just interchange. So that's 2 pi over what? Over omega. That's our time in what? In seconds. Just like that. So guys, learn to play around your formulas. So we've got the period there. This time that you're talking about is the period. So I think that's it, guys, from, all right, since we talked about radians and degrees, remember from your N2, guys, N3, that we can have the complete cycle, 2 pi being 360 degrees, all right? So this is in radians and this is not in degrees. This is from a complete revolution, one revolution, or a complete a complete revolution, complete cycle. So you're talking about one revolution here. So dividing by 2, you're going to have pi. Divide by 2, you're going to have what? 180. So you can also use this. Pi is equal to 180. Or we can have it from 1 radian, 1 rad as it is to the degrees. It is equivalent to 57.3 degrees. So conversion, it's in your hands. So meaning to say, where we want to convert the radians to degrees, we multiply by what? 57.3 in short, if you want to use this one. That is what it simply means. You can convert radians to degrees. So guys, conversion is in your hands. You can use this part. You can, guys, any part that you want. So I think with this information that we have, let me just list some of the formulas. But this is, guys, like this is just like a recap of what you had before. It can maybe just help some others to just remember what you had before. Remember, from these, you work with values, maximum, from the maximum value, our Emax or this Xmax that we are seeing there. We can have average values from there. We can have the RMS values. There are so many things, all right? So let us start with average or the mean value. So the average or the mean, remember average, that's mean. The average or the mean value can be determined if you are having the maximum value. The average value can be calculated as 0.637 of the maximum value. So if it is current, meaning to say we have the same thing there. We have got the same thing. We're going to multiply to the maximum value. So this is a constant that has been calculated from your integration, guys. That's another part that you are going to see later on from your integration. So I'm not going to dwell much into that one. I just need you to know the formulas, and also you've got that one into detail from your formula sheet. And also the RMS value can be determined. So the RMS value is the value that we have as the effective value of an alternating quantity. All right. The effective value of an alternating quantity is the value of a DC quantity that produces the same amount of heat in the same time. So that's the idea of our RMS value. So if you are talking about ERMS, that is also from your integration. So that's 0.707 times the maximum of value. Therefore, if it is the current, we've got the same thing, guys. Same thing, even for the current. So I want you to just understand these basics as an individual. Then number 3, we also have the form factor. So that's the form factor. So the form factor is a ratio. This is ratio of RMS value to its average value, this one. So this one is a ratio, of the RMS value, okay, of the sine wave of the given wave that we are given, all right, of a wave to its average value, of what? Of the wave. So meaning to say, if we are saying it's a ratio, this form factor, that's KF. So F for form, right? Form factor. So factors, they are represented with a K. So the one form factor, so it's going to be KF. So KF as our form factor is simply a ratio, as we said, RMS value. So it is supposed to be like this: RMS value to the what? Average value. So that's the idea of our RMS, of our form factor. So meaning to say, if you're working from the EMF, it is going to be ERMS over E average. If you're working from the current, it's going to be RMS of the current to the average of that current. That's the idea, guys. Just like that. So like I said, this one is just a recap. Then we also have the crest factor. The crest factor. So this one we're gonna have it as KC, crest factor. So the crest or the crest factor, I mean, is taken as the maximum value of the wave to its effective RMS value. So it's also a ratio, that one. So it is the ratio. So this one is the ratio of the maximum. So I'm just going to write in short here, of the maximum value. All right, let me just write in full, guys. Some of us might need this. Maximum value of the wave. So this is the maximum value of the wave to its effective RMS value. To its RMS value, which is the root mean square, the RMS root mean square. So this is simply a ratio, just like the previous form factor. It is the same thing with our crest factor. So meaning to say, the crest factor can be written as from the maximum. So it is simply maximum value over what? The RMS value. So if, let's say, I'm working with the EMF, it's going to be Emax over what? Its average, its RMS value. If I'm working with the current, its maximum value to its RMS value. So these are factors that can be determined. And with these, we actually do understand, guys, that we calculated, remember, if you've got, if you go back to these values, you substitute, we saw that the form factor at the end is going to be equivalent to what? 1,11, only for a sine wave. So this is going to be for a sine wave. For a sine wave. So we proved this one, I think, even in industrial electronics. So guys, I'm not going to take much time on this one. You can go back. I did these videos on N2, so you can watch them. And also this one, we proved it to be 1,414, only for a sine wave again, for a sine wave. So these are the other things that you just need to understand as an individual. So from a sine wave, that is, these formulas, they are not useful. They are useful if we are dealing with a non-sinusoidal wave. That is where these formulas can be used. Because if you know that it's a sine wave, you just know the answer is going to be 1, for the crest factor and for the form factor. All right. So this is what we have, guys. As we can see, the sine wave, we have the maximum value. We can see it from the mathematical presentation. It is already available. We can see it. But if we have this one now of a non, because that is a sine wave that we have, that we just had, it was a sine wave. So let's say now we consider a non-sine wave, which is a non-sinusoidal waveform or waves, such as rectangular. These are the ones that we can consider. It is not having the shape of a sine wave. That's where we have got those rectangular, sawtooth, and so on. Those ones, we are not going to be given the maximum values. No. They are not going to give us maximum value to say, okay, this is the maximum value. So from that maximum value, now calculate the average value. No. They are going to give us midpoints. Remember, from your N2, you are going to calculate the RMS value, the average value from midpoints. From midpoints. So if we are given the midpoints, let's say we are given those midpoints, that's where you're going to be given that table showing you the midpoints. Remember your previous levels, guys. So we said in that case, if it is the average value, let's say for the EMF, the average value is going to be taken is E1 plus E2 plus E3 and so on, plus the last one that you're given. Everything you divide to the number of those midpoints. So you're going to divide by n. So this n is the number. All right, let me just write in short, number of what? Mid coordinates or midpoints. This is the idea here. And these are the mid ordinates that we are seeing here, the E1, E2, and so on and so on. These are the mid ordinates. So guys, that's the idea there. Or the midpoints that you are given. The midpoints. So if it is current, you're just going to have the same idea for the current. That is what you have. We also have the average, I mean the RMS value. If it is the RMS value, meaning to say this one is going to be ERMS, that will be the square root of, so this one will be the square root of, you square these ones. So it's E1 squared plus E2 squared, E3 squared plus, and so on and so on. And the last one also has to be squared over the number of those mid-ordinates or midpoints. So that's the idea. For the form factor, the crest factor, we use the same concept that we had here as we calculated, as we had these formulas for the form factor, RMS value for the form factor to the average value. Then the crest factor, the maximum value to the RMS value. Only that for a sine wave, that's where we have a direct answer. But if it is for a non-sine wave, for a non-sinusoidal wave, we must go back to the proper formulas. Even for this, we're going to use these formulas. The crest and the form factor, we use these formulas here. That is the idea. So please do make sure that you go through your questions, understand idea of how the questions are being given, and playing around with questions. Let's say, for an example, we are given the RMS value. We calculated it. We can calculate the maximum value because there is a relationship between the RMS and the maximum value. Remember, when we talked about this, we can also have the maximum value as the subject. Remember, I said when you are given mid-ordinates or midpoints, they do not give you those maximum values. So you're going to make maximum the subject of the formula. If it is current, the subject of the formula from the average value or from the RMS value, depending with which one that you are capable of, you're going to have same answers from there. So that is it, guys, on this part. I want you to go through these formulas and the basics of what you had before. Answer questions with this information or with these notes that you have. You can answer as many questions as you can. Remember, we said the whole of this part here, if it is in radians, it can be converted to the degrees because it must be same units. So when you change the whole of this part. So meaning to say, if you are someone, you are going to multiply by 57.3 degrees, the whole of this part, if you want to convert to degrees. It depends with the question, how it is given and how do you want to convert, guys. It's not about the textbook. The textbook is converting like this. What about you? How do you understand that conversion? Yes, the textbook is a person, just like you. That person has got his own understanding or her own understanding. What about you? What's your own understanding in that mathematical view that you are given? So I want you guys to play around with these formulas. It's only that we do not have enough time for each trimester that we have. But otherwise, I wanted you as an individual to understand the formulas, playing around those formulas so that you can answer the question in the way that you understand. Not to say you follow up the memo, it's like this. No. What about the way that you understand? So we're going to have another class working with the questions and just see a basic view of how the questions might be given as. So make sure that you become part of the membership so that you do not miss any of the other classes that we are going to be having till we meet again.